Driven by the insatiable curiosity to explore the secrets of the universe, humanity has embarked on a journey that defies the boundaries of time, seeking answers to the questions that haunt the fabric of reality. Remarkably, the James Webb Space Telescope, with its piercing eye, has just captured a glimpse of a cosmic structure that precedes the birth of stars, a celestial anomaly that appeared to be older than the universe itself. You might be wondering, how could a structure be older than our universe, or is the Big Bang theory flawed? Join us as we explore how the James Webb Telescope just detected a 13.8 billion-year-old structure and its far-reaching implications. Imagine gazing at the immense cosmic realm, where stars and galaxies perform a dazzling dance of light and gravity, revealing the secrets of the past and the future. This is what the James Webb Space Telescope, a spectacular space probe, does every day, capturing and transmitting its breathtaking observations to Earth. Recently, it has unveiled a mystifying spectacle, a 13.8 billion-year-old celestial structure that defies the very foundations of our cosmic comprehension. Through this remarkable technological marvel, we are faced with a profound cosmic mystery, a mystery that is intricately woven into the very fabric of space itself. This shocking discovery has ignited a storm of debates and explanations within the scientific community, as they try to unravel the paradox of this ancient structure. Renowned scientists and notable observatories around the world are constantly flooded with questions about this perplexing phenomenon. The most popular among these questions is, how can the James Webb Telescope detect a structure that is older than the universe itself? To answer this question, we need to first zoom in on this structure. It is not a galaxy, or a nebula, or a black hole. It is a star, a very old and very special star. It is located over 200 light-years away, near the constellation Libra. It is called HD 140283, but it has a more fitting name, the Methuselah star, after the biblical figure who lived for 969 years. This star is not only ancient, but also fast. It zooms through space at a speed of more than 800,000 kilometers per hour, revealing its dramatic history some 12 billion years ago, when the precursor of our Milky Way galaxy devoured a dwarf galaxy, which was its original home. However, what makes the Methuselah star truly fascinating is not its speed, but its age. It is one of the oldest celestial objects we have ever observed, and its age defies logic. According to the initial estimates, the star was around 16 billion years old, but the most recent estimate is 14.46 billion years, with an uncertainty of 0.8 billion years. This figure poses a puzzle because the age of the universe, as determined from observations of the cosmic microwave background, is around 13.8 billion years. How can a star be older than the universe itself? It seems impossible. This paradox led to questions about the star's age, the universe's age, or the accuracy of dating methods. Could the star be a remnant of a previous universe? Could the universe be older than we think? Could our dating methods be flawed? Let's explore these possibilities further. First, we need to understand that measuring the age of celestial objects is a daunting task. Stars like our Sun maintain their brightness, temperature, and size for billions of years, making age estimation difficult. Astronomers rely on subtle changes in brightness and color over time and compare these measurements to mathematical models that predict how stars change with age. One key indicator of a star's age is its spin rate. Over time, stars slow down their spinning, similar to a wheel slowing down due to friction. By comparing the spin rates of stars at different ages, astronomers have established mathematical relationships to estimate their ages, a method known as gyrochronology. Another indicator of a star's age is its magnetic activity. Magnetic activity, like flares and bursts of energy on a star's surface, decreases as a star gets older. Astronomers have developed advanced techniques such as astroseismology to study vibrations on a star's surface caused by waves traveling through its interior. These vibrations change with a star's age, helping to estimate its age more accurately. For instance, using this method, astronomers have estimated the Sun's age to be approximately 4.58 billion years. Returning to the Methuselah star, astronomers assign such an ancient age to it by considering the population of stars it belongs to. Stars in the universe can be categorized by the amount of heavy elements or metals they contain. Our Sun is a population I star with a significant amount of heavy elements. In contrast, the The Methuselah star is a population 2 star with fewer heavy elements, particularly iron. This means that the star was born before most of the heavy elements were created in the universe, which happened in the explosions of massive stars called supernovae. There is also a hypothetical class of stars, called population 3 stars, which are believed to have virtually no heavy elements at all. These stars are thought to be the first ones that formed in the primordial universe, shortly after the Big Bang. They were extremely massive and hot, and they burned their fuel very rapidly, turning hydrogen and helium into heavier elements. When they die, they explode as supernovae, scattering some of these elements into the surrounding space. Population 2 stars emerged from the gas clouds that were slightly contaminated by these elements, while population I stars originated from the gas clouds that were further enriched by subsequent supernovae. The existence of the Methuselah star poses a perplexing question: how can it be older than the universe itself? The answer is not simple, as it involves a lot of uncertainty and assumptions. Based on the measurements from the Hubble Space Telescope, there is a 70% probability that the Methuselah star's age ranges from 13.66 to 15.36 billion years. The lower bound of this range is consistent with the estimated age of the universe, which is about 13.8 billion years. However, there is also a 30% chance that the star's age falls outside this range, with a 15% chance that it is even lower. Considering all the factors, there is at least a 20% possibility that the star's actual age is younger than the universe's age. This is like rolling a standard 6-sided die and getting a 6, which is not very unlikely. But this also assumes that there are no other sources of error or bias in the age estimation. Nevertheless, it is undeniable that the Methuselah star is incredibly ancient. In fact, it is the oldest star in the universe with a reasonably accurate age determination. Rather than wondering if it could be more than 2 billion years older than its environment, we can approach the problem from a different angle. Could it be that the universe is not as young as scientists initially thought? In reality, it is hard to grasp the enormity of 13.8 billion years. If we compress the entire history of the universe into a cosmic calendar, with the Big Bang as the most dazzling New Year's fireworks, Earth would not show up until late December. Recorded human history would only span the last 10 seconds of December 31st. Scientists calculated the age of the universe by observing the light from stars that were born just a few 100 million years after the Big Bang. As the universe expands, it stretches this ancient light, making it redder. This is called redshift. By measuring both the distance and the redshift of these stars, scientists can infer the age of the universe. However, recent findings from scientists at the University of Ottawa suggest that the universe might be much older. They propose that it could be around 26.7 billion years old. Rajendra Gupta, a physics professor at the University of Ottawa, brings up an old theory from Swiss astronomer Fritz Zwicky, dating back to 1929. This theory claims that photons lose energy as they travel across enormous distances and time. This contradicts the observable redshift data, but Gupta argues that by accepting this theory along with the expanding universe, we can view redshift as a mixed phenomenon that is not only caused by expansion. Increasing the universe's age could shed light on some long-standing cosmological puzzles, as well as some new ones raised by NASA's James Webb Space Telescope. Gupta arrives at the age of 26.7 billion years by combining the tired light theory with the idea of evolving coupling constants, first suggested by theoretical physicist Paul Dirac, which means that particle interactions may have varied over time. It is important to note that scientists have changed their estimates of the universe's age before. For example, in the 1920s, Edwin Hubble thought the universe was only 2 billion years old. However, our methods have become more accurate over time, and doubling the universe's age is a huge jump. It remains unclear whether astronomers will change their views on the universe's age based on Gupta's work. But no matter if humanity's recorded history is equal to just 10 or 5 seconds in the grand scale of the universe, one thing is certain: the universe is an ancient and magnificent place. Shifting our focus from the age of the universe, there are some fascinating observations about the Milky Way. Recent measurements show that stars at the edge of our galaxy are moving much slower than stars in similar locations in other galaxies. There are a few possible reasons for this phenomenon. One is that our galaxy may have a very low amount of dark matter, which is the invisible substance that affects the gravitational structure of cosmic objects. Another possibility is that our knowledge of dark matter, including how much there is in the universe, may be completely wrong. This mystery stems from data collected by the European Space Agency's Gaia satellite, which gives detailed information about the speeds and positions of nearly 2 billion stars in the Milky Way. These accurate measurements have made astronomers rethink their evaluations of stellar behavior across the galaxy. Several research groups have now reported the slower orbits of stars along the Milky Way's outer edge, questioning our previous beliefs. The speeds of stars help us estimate a galaxy's mass. The faster they are, the more mass the galaxy must have to keep them from flying away. The mass of the galaxy includes not only the visible gas, dust, and stars, but also the mysterious dark matter that makes up most of the matter in the universe. A recent study using data from the Gaia satellite estimated that the total mass of the Milky Way is about 200 billion times that of our Sun. This is an impressive number, but it is also surprisingly low. It is about 5 times lower than previous estimates based on other methods. How can we explain this discrepancy? One possibility is that the Milky Way has much less dark matter than we thought. Since the visible material has not disappeared, this would imply that the dark matter is either more elusive or less abundant than we assumed. This would have profound implications for our understanding of the nature and origin of dark matter, as well as the formation and evolution of galaxies. But before we jump to this conclusion, we need to consider another possibility, that the measurement of the galaxy's mass is not accurate. Measuring the weight of a galaxy is a notoriously difficult task, as it involves many uncertainties and assumptions. The data from Gaia, which is a space telescope that maps the positions and motions of billions of stars in the Milky Way, is the most precise and comprehensive ever collected. However, it is still not perfect, and it may contain errors or biases that affect the analysis. Moreover, different research teams may use different methods and models to interpret the data and infer the galaxy's mass. The fact that several teams have reached similar results using Gaia data gives some confidence to the findings, but it does not rule out the possibility of systematic errors or alternative explanations. If the low mass estimate of the Milky Way is correct, it would challenge our current theories of physics and cosmology. It would mean that the Milky Way is an outlier among galaxies, having much less dark matter than expected. It would also mean that we need to revise our estimates of the mass of other galaxies, which are often based on comparisons with the Milky Way. As Stacy McGarr, an astronomer at Case Western Reserve University who was not involved in these studies, says, if it turns out this way, it would be revolutionary. The origin of this puzzle goes back to the 1970s, when astronomer Vera Rubin and her team made a surprising discovery. They observed the motion of stars in other galaxies and found that they did not follow the expected pattern. They expected that stars farther from the center of a galaxy would move slower than those closer to the center, just like the planets in our solar system. However, they found that the stars at the outer edges of galaxies were moving almost as fast as those near the center. This implied that there was a huge amount of invisible matter in and around galaxies that provided extra gravity to keep the stars from escaping. This matter was dubbed dark matter, and it was estimated to form massive halos around galaxies, outweighing the visible matter by a factor of 10 for large galaxies and up to 100 times for dwarf galaxies. Measuring the motion of stars in our own galaxy is not easy, as we are inside it and cannot see it from a distance. Therefore, astronomers often assumed that the Milky Way was similar to other galaxies and had a large amount of dark matter in its halo. For example, the Sun, which is about 26,000 light-years from the galactic center, orbits at a speed of about 800,000 kilometers per hour. Most observations of stars in the Milky Way and beyond supported the idea that the speeds of stars at greater distances from the center would be roughly the same as that of the Sun. The Gaia satellite, launched in 2013, offers the best test of this idea so far. It provides extremely accurate measurements of the three-dimensional positions and movements of stars in the Milky Way. This allows astronomers to map the structure and dynamics of our galaxy with unprecedented detail. As the Gaia mission progresses, the precision of its measurements improves with longer observation periods. Using Gaia data, theoretical physicist Francesco Silos Labini from the Enrico Fermi Study and Research Center in Italy and his colleagues detected subtle signs of a decrease in the speeds of stars in the Milky Way a few years ago. These signs became more evident in Gaia's latest data release in 2022, which has twice the precision of the previous data from 2018. These improvements allow astronomers to plot the paths of stars more accurately and over much greater distances. In this year alone, four different research papers have reported a significant decline in the speeds of stars up to 100,000 light-years from the center of the Milky Way. The recent study in astronomy and astrophysics calls this slowdown Keplerian, after the 17th-century German astronomer Johannes Kepler, who first described the motion of planets. This is a surprising finding, because it goes against what we see in other galaxies, where stars from the center to the outer edges move at similar speeds, as if they are pulled by the gravity of dark matter. Why is the Milky Way different from other galaxies? This is the question that François Hammer of the Paris Observatory, co-author of the recent astronomy and astrophysics study, raised. He wonders if the Milky Way is unique among all galaxies, which would challenge a fundamental principle of cosmology, which states that no place in the universe is special. The slowdown of the stars in the Milky Way also implies that our galaxy is much lighter than we thought. A recent study using data from Gaia estimated that the total mass of the Milky Way, including gas, dust, stars, and dark matter, is about 200 billion times that of our Sun. This is impressive, but it is also about 5 times lower than earlier estimates based on other methods. Astronomers are confident that they have measured the visible material in the Milky Way correctly, which accounts for about 60 billion solar masses. If both of these numbers are accurate, it means that the ratio of dark matter to ordinary matter in our galaxy is only 2.3 to 1, far lower than the 10 to 1 ratio seen in galaxies of similar size. So, is the Milky Way really so light on dark matter? Not all astronomers are convinced that the slowdown of the stars represents the whole picture. Some of them suggest that stars farther out beyond Gaia's high-precision range could show an increase in speeds to balance out the unusual drop. Astrophysicist Lena N.B. of the Massachusetts Institute of Technology, co-author of one of the papers on the slowdown of the stars, says, "I'd be very surprised if it just keeps going because then there'll be a lot of things that break all at once." She points to various pieces of evidence that support a heavier Milky Way. One of them is the Large Magellanic Cloud, a satellite galaxy that orbits the Milky Way at a distance of about 160,000 light-years from the galactic center. It moves at a speed of over 650,000 miles per hour, which is consistent with standard dark matter models. Another piece of evidence is the stellar streams, which are the remains of smaller galaxies and star clusters that were ripped apart by the Milky Way's gravity. These stellar streams stretch to great distances and give estimates of our galaxy's mass that agree with the heavier estimates. There is also the possibility that the different research teams are somehow misinterpreting their data. Astronomer Robin Sanderson at the University of Pennsylvania creates simulated Milky Ways on a computer and imagines what kind of maps a virtual Gaia satellite would make if it were inside them. She notes that these maps depend on certain assumptions that can affect the results, such as the overall shape of the galaxy's dark matter distribution. Sanderson, who was not involved in any of the papers, is skeptical about drawing firm conclusions from the existing data. She emphasizes that while Gaia provides unparalleled 3D information, the uncertainties in its measurements of stellar speeds increase as it observes stars farther from the galactic center. Future observations from other telescopes, such as the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, may be able to find more stars in the outer regions of the Milky Way that can help resolve the controversy. Gaia's next data release, expected in late 2025, may also provide more precise and comprehensive information. In the meantime, researcher Hammer is keen to examine other galaxies more closely and see if they show similar declines in their stellar speeds. This episode is a normal and healthy part of the scientific process, as it takes time and effort to reach a consensus. But the Milky Way mystery is not the only one that puzzles us. The universe is full of enigmas that have fascinated us for ages. From our solar system's backyard to the farthest reaches of the cosmic ocean, these mysteries have always captivated our curiosity. Centuries ago, ancient astronomers wondered about comets and the composition of stars. While some of these old questions have been answered as technology advances and our instruments probe deeper into space, new mysteries keep emerging. Despite the incredible progress we've made with computers, the global internet, and space observatories that map the distant corners of the universe, we still have much to learn. Even in this age of significant scientific advancement, we find ourselves with a vast portion of the cosmos, 95% still shrouded in mystery, either unseen or not yet understood. We've come a long way since the days of ancient philosophers and early astronomers like Ptolemy and Kepler. However, in many respects, we remain newcomers striving to comprehend the mysteries of the universe. At the end of the day, we inhabit a solitary planet suspended in the vast expanse of space, orbiting our sun amidst a multitude of stars in a small corner of the galaxy within an ever-expanding universe. Humans have an inherent drive to seek meaning in the stars, even though the answers may not always align with our initial expectations. This quest for understanding is what drives the scientific exploration of the cosmos, and it's a journey that continues, unveiling new questions as it uncovers answers. What are some of the questions that you have about the universe? And what are some of the mysteries that you would like to see solved? Share your thoughts and opinions with us, as we explore the wonders and the secrets of the universe. Thanks for watching, fam. For more mind-blowing discoveries, click now on the next video you see on your screen.